definitely the coolest stuff is the applications of alpha decays. And I'm really only going to give two, but I'll tell you one thing, there's a lot of them, and they're really, really awesome. I think radioactive decays and how they, they work in our world is quite amazing. So the first one is aramecium. Oh, I always get the I in the wrong spot. So aramecium, this guy is 241.95. And what you see here is radioactive. Now, why do we know it's radioactive? Because its atomic number is larger than 82. So if I look at this thing, I'm seeing that the atomic number 95 for is greater than 82, which is lead, the last stable element. So what this tells us here is that this must be manufactured. You do not find this on Earth. You cannot go mine this. In nuclear accelerators. And everybody has it in their house. Everybody has it in their house. Now, what is it that's in your house? Well, aramecium is part of a sensing circuit in smoke alarms. And maybe I should smoke alarms, smoke detectors. And so what you're seeing here is that, I mean, I know that all modern homes are automatically equipped with smoke alarms. Older homes, they recommend that you put them in. So they're part of the circuit. And what you find here is that you have a source and a sensor, and there's a stream of particles that happen. So let's go look at this thing here. So what you find here in smoke detectors there is a source. And what's the source? Well, it's 241 aramecium, which emits alpha particles. Okay. And a detector of alpha particles. So what do I mean here? So when I think about a smoke alarm, it does this type of thing. I imagine that I have a source like this. And typically when you look at alpha sources, they're color-coded. And that the reason why they're color-coded is that it's sort of like a very common thing when you're looking to try to distinguish between alpha, beta, and gamma. So it turns out that an alpha source is red. So this thing right here, this is the source of alphas. In other words, 241 aramecium. And so what you're finding here is that it is literally shooting alpha particles. So they're shooting them. And what they shoot them at is that they shoot them at a detector. I can actually, yeah, let's leave it right there. And so here in the detector, what you're finding at is this guy right there. So this guy detects the stream. Wow, I don't even know how to spell stream, I guess. Stream of alphas. And what it does here is that when it does that, it knows the number of alphas since it's a counter. So it's literally counting the number of alphas. So the key thing here is that if this number is constant, then there is no alarm set off. Okay, there's no alarm set off. Now, here we go. So a house is on fire and produces smoke particles. And you got to remember that alphas are really easy to stop, right? And so what I'm asking you to do here is that remember, even paper stops alpha particles. So remember, alpha particles are very easy to stop. So they will never penetrate your skin, never. So then here it goes. So now what happens is that I have my smoke detector. And so if I have my smoke detector here, what happens next now is that I have a series of smoke particles that are now in the way. And so what you're seeing here is that with smoke particles, in between the source and detector, the number of alphas is drastically reduced. And as soon as it's reduced, it then says, hey, smoke is here, so therefore alarm goes off. And that's the way a smoke detector works. It's a very, very, very different, process, but quite easy here. So if we then go and look at aramecium, what is aramecium doing? So what we got to do here is that then we can go and look at the particles here. And what you find here is that you have this question. what is the daughter of 241 aramecium for this decay? So then if I look at this, we know that it's 241. And then what we're going to do here is that we know this goes by an alpha decay. And if it goes by an alpha decay, we know that the alpha is going to take 4 and 2 like this. So then that means that when I look at this thing, that means that the original aramecium now magically changes using this right here. Okay. And so we don't know what this guy is. So we'll have to figure it out. And then, of course, you have the energy that also leaves here. So then what I got to do here is that we can see here is what this is telling us is that our new nuclei or atom must be 237, 93. Why? So that means here is that we need to look at the periodic table. So if I look at the periodic table, I'm just going to say that I just went onto the periodic table and I looked to see which was atom 93, and here it is. It's atom 93 is Newtonian here. And so when I look at the full decay here, what am I seeing at the full decay? So the full decay then is that we now know is that now we have our alpha. And now we know that this is 237, 93 Newtonian plus the energy. And so this is the kind of thing that I would ask you to show me on a quiz and an exam. So, but the important thing here is that we need to have this in the language of this thing, right? This is the important piece here. This is the important piece. So where does this thing stand out? I think this might be too big. I'm hoping it's not. Okay, I think that's okay. So I'm going to move this up just a tiny bit here. So if I look at this, I got to go look at 95. Now remember, we have to estimate what 95 is. So I'm just going to roughly guess. So I'm going to say that 95 aramecium is somewhere up here. So it's got to be in the yellow region right here. So here I am. It's right there. So if I look at this, this is aramecium 95 right there. And then, you know what? I don't want it here because that's going to interfere with what I'm talking about. So I'm going to move this guy over here. I wasn't really thinking. And then what's going to happen is that there's going to be a jump. And I'm going to say that it's going to jump right here. And this is going to be Newtonian, which is 93. So look what's happening. Look at the jump. You don't see a jump up. You only see it jump down. So it jumps down, never up. So what do we know here? There's a couple of things here. We see here is that once again, the alpha decay is moving 241 aramecium towards the black line of stability. However, its daughter, 237 Neptunian, oops, it's with the P, not with the N. That's neon, is also radioactive. Why is it radioactive? For the same reason aramecium is radioactive, because why? It's heavier than lead. And because it's heavier than lead, it's radioactive. So then that means here, because it's radioactive, it will continue moving down via decays until it reaches the black line of stability.